All right. So yeah, I mean, the title, as you can see, the title advertised creating a million virtual thread using Project Loom to improve throughput. So I'll focus on that part, which is throughput. Before going into the serious talk, let me introduce myself a bit. I am a software engineer currently working at Concurrency Security. I'm a Java Azure Group leader at Bangladesh Java Azure Group. So I've been doing it like since 2013. And then I moved over here. Although I'm not physically there, I do virtual events nowadays. So there are folks over there, so you could constantly communicate with them. So apart from that, I write. Obviously, as you mentioned, I'm an InfoQ editor. I write on Dijon, and also I'm an editor of Foji.io, which is a new things. Recently, it's been here like a few years. But it's a dedicated blogging platform for OpenJDK. So if you are enthusiastic of Java OpenJDK, you can go there and write content, and there are a lot of contents over there. I also write books. I have written 4 books on Java programming on my native language, which is Bangla. So a lot of folks over there back home read my books, and some of them are bestseller. Obviously, not in Bangladesh, basically. So since they are written in Bengali. All right. So recently I have been given the honor of, Java champion. So I am deeply honored by that. So that's all about me. If you find it boring, let me move into the agenda directly. So what I'm gonna do over here is, I'm trying to give you a bit of context. What is Java concurrency all about, and if there is any problem with existing concurrency model, because we have been doing it for like last 27 years, and why all of a sudden we need a new paradigm, which is virtual thread, and what does it make even sense, and if there are any limitations. So keep in mind that this is going to be extremely high level, because the project Loom is not still out there. It's in preview feature, where it's still it's still actively being developed. So if you want to try out and find things, you can give feedbacks too. So still it's not production level things, but as a developer, I'm extremely excited about the the concept, the idea, about the thing itself. So yeah, bear that in mind. And the other thing is, I'll try to make it interactive. So if you have questions, feel free to ask anytime, and I'll pause and try to accommodate the answer if I know. If I don't know, then yeah, that's also good things that in fact give me an opportunity to research and then find the answers. Hopefully I'll be able to share that later. So that's the agenda. Moving on. So like I said, I'm gonna give you a context. What is concurrency all about in Java? Probably you have been Java developer for many years, I'm pretty sure, and you already know this, which is Java is pretty much made of thread. What do we mean by Java is made of thread? I'll give a context in shortly. So from day 0, Java introduced thread. Thread is basically if you can think it is as an execution environment or unit of execution in Java. That means whatever code we write doesn't matter. It can be single line to millions of lines. It's going to be executed by a thread. That's how Java is designed and developed, and that's how we used. Even though as a developer, if I don't deal with concurrency, for example, it could happen that I'm a developer and I'm just writing mundane Java codes. It happens, right? I don't deal with concurrency at all. It's true for many developers. So still you are doing concurrent programming in Java, because Java is basically whatever code you execute, it's going to execute by a particular thread. So now that we established the fact that Java is made of thread, and any code that we write are going to be executed by a thread, and it's an execution environment. What if we have more execution environment, right? So that means if we have more threads, that gives us more execution environment. And if we have more execution environment, that means we can do things simultaneously. And there are certain benefits of doing things simultaneously. For example, think about a GUI library, right? You press the button and then something happens. Let's think about a simple calculator, right? You press the button and it does the calculation, right? And if we can do two things simultaneously, then you can press perhaps two buttons at the same time, right? You press one button and then press another button, and something is happening in the background as well. So that gives us responsiveness, and also, we can make progress multiple things simultaneously. So that's a huge benefit, and we have been using this benefit for many years. All right. So like I said, Java is made of thread. Even if you run a simple hello world program, for example, this curly brace to this curly brace, right? It's a simple program. It just print a hello world on a screen. It also run by a thread, and if you do the thread dump, you'll be able to see that. And this is the main method is since its name is main, historically the thread name also main, interestingly. So it's executed by main thread, and you can create other threads from the main thread. That's interesting. All right. So apart from that, Java, I mean, if you want to see the exceptions and stack trace, those are also means we get those by means of thread, right? Thread is store all these stack trace, and then we can print them or we can analyze them, whatever we want to do that, right? So if we need to debugger, that's threads. We need threads. If we need to profile and all sort of places, basically we use threads. So again, I'm just reiterating the information I shared the earlier slides. So far we established the fact, right? So moving on. Now, how do we create threads basically in our applications? Typically, we are going to create like a new we'll create a new instance of thread. Thread is basically a wrapper of a native thread. What I mean by native thread, I'm going to come in a minute, but this is how we create threads, programmatically. So we'll create an instance of new thread, and we'll provide a runnable. Since 8 we have lambda expression, we can provide lambda expression as well, which is I have used over here, but you can provide a anonymous inner class as well, which is an instance of runnable, right? And then whatever you put inside that runnable is going to execute by this particular thread, and then you can start the thread. So that's how we basically create threads. Now you have to keep that in mind that in Java, Java is thread is not Java construct. It's basically a mapping of operating system thread. So operating system provides us a amount of threads, or we can request from Java. We can request to give us a thread. So that's how it works. So when we create a new thread, we basically ask operating system give us a thread, or create a new thread and give us to us, and our class, which is thread java lang.thread, is basically a mapping, one-to-one mapping. It's a thin wrapper. So keep that in mind as well. So when we create new threads, we basically get a thread from operating system. And creating threads, that's why it's a bit expensive. And when we call thread.start, it is also considered inefficient because it requires native calls, and it takes time, and the other things. Also, it takes some memory as well. For example, when we create a new thread, it takes around 2 megabytes of memory outside of the heap. So let's say if your operating system has 8 GB of memory, and you give you give half of them as a heap space, right? So like 4 GB. Now the other space is available for operating system and other things. And if you create a new thread, basically, outside of our heap area, you're going to create a new allocate new memory, which is 2 megabytes for each one. And so that means we cannot create a lot of threads. if we want to create like, the advertisement of this stuff, like I said, we can create 1 million of virtual thread, but in reality, let's forget about virtual thread. Let's think about a regular thread, day-to-day thread that we use in our applications since the birth of Java. We cannot create millions of threads. It's practically impossible. For example, if you want to create 1 million of thread, it would require like 2 terabytes of memory, which is pretty close to impossible, right? Theoretically, probably possible, but then again, when we are too many threads, we also requires to context switching, right? So let's say we have 8 threads. It's easier because if we have like 8 core of machine, which is pretty usual nowadays, then each of core can run each thread continuously. But if we have hundreds of threads, we need the operating system going to switch the threads with algorithms. For example, operating system have this thread scheduling algorithm. It can be round robin, and other means it can be priority based. But essentially, if we have 8 core of machine, if we have a machine with 8 core, basically at a point of time, machine can execute 8 threads, right? So we're not going to give one thread like forever, right? We're going to give a small amount of time to execute particular thread to do his work, and then switch and give another thread so that everyone get the opportunity to be executed. So that's what happened in operating system. And the context switching basically requires some times, which is close to 100 microseconds. It seems a little, but if you have a lot of threads, that adds up. And so that's why it doesn't always make sense that if we have too many threads, we will definitely have too many execution environment, but that doesn't increase overall performance of the application, because thread takes memory, also it requires context switching. So we have to keep those things in mind. All right, so these are the problems, right? With traditional threadings. So moving on, now think about our modern applications. Especially if it is a web applications, how we deal with multiple request response from a client. So we do it traditionally, the servlet spec we have, what it does is whenever a request comes to a server, it gives that responsibility to a thread. And this particular thread basically do all this work and then send a response. So another request comes, it gives the responsibility to another thread. This is what happens in our modern web applications. So basically each request gets a thread. And that's why in our modern application web server, we pull threads, right? We will create like 400 of them, and they will, each time a new request comes, they will just give one thread to each request. So that means let's say we have 400 threads right now, and we have like 400 requests at a moment of time, right? That means we have our throughput is sort of limited by the number of threads we can have. And the problem is with that notion is so when we get a request to an application server, the application needs to communicate with other services, for example databases or another microservices, and these are IO intensive operation, right? So now that, let's say we need to communicate with the database, and database takes some time. So it's happening in different processes. But the particular thread that I'm allocating, I'm giving the responsibility to talk to the client. He receives the request and he is processing, and then after a certain time, it query a database, and database is taking time. Meanwhile, it has nothing to do, right? It's just waiting to get the result from the database. Once it gets the data, it doesn't do anything. Meanwhile, it's just idle waiting to get the data, and once it's done, it's send the response, and then it's relieved to get another, to serve another request. So think about the scenario. We have 400 thread in a application server, and we have 400 requests. Similar the scenario I have just explained. So most of the time, those threads are basically blocked. if we have a IO intensive operation like talking to database, talking to other microservices. So even though we have 400, which is many, and but most of them, they are basically blocked or waiting to get result, right? So we are wasting, in a way, we're wasting CPU. So that's one problem. The other problem is our throughput now are sort of limited by the number of threads we can have. 400, that means we cannot get more than 400 requests served at a point of time, right? So that's also limit our throughput. But as if your application is popular and it becomes a lot of users are going to come in your applications, right? You need to scale up, right? You definitely want to have a lot of throughputs. You can, as much throughput you can achieve, the performance of overall applications is more, right? And that's why we created too many applications. Sorry, not too many. I mean, the copy of applications. We keep like multiple copy of applications so that we can accumulate the throughputs. But while we're doing that, we have a solution over here. The problem is, although we are solving this problem by this this way, but meanwhile we're wasting our resources as well, because our threads are pretty much wasting time, wasting on waiting on something else, which probably we could utilize that. So all right, and the other thing is our modern operating system can handle theoretically millions of concurrent connections. So you can just tweak that. We can create like millions of sockets. So the idea is, if our modern operating system can receive requests, can have a million socket, that means it can receive theoretically 1 million requests. The problem is we cannot serve 1 million requests because we are limited by the number of threads. So if we could have millions threads running on our applications, and each request is served by each one thread, theoretically we can have millions throughputs, right? Does that make sense? But again, we can have that much of throughput, but again, we are limited by the number of threads we can. Now the question is, how many threads we can in fact create? So I did a little experiment with this simple code. You can take it and try on your machine as well. So what I did is, in a while loop, I just keep creating threads and see how many threads we can create. Any guesses how many threads we would be able to create? Anyone? Take a wild guess. Doesn't have to be accurate. All right, I've got 1,000. Okay. Anyone else? All right. So I can show you my number over here, which is if you run this program, after a while you will get this exception. So out of memory, since you don't have unlimited memory, right? After a while, your application will throw these out of memory exceptions. And since I was counting and printing, so I was able to get like 16,000 of my thread. And the spec I have, which is I had a 16 GB of memory available on my local machine. So that's why the count is large. Usually the application server or the typical typical web applications server where we host, it doesn't have this much memory, right? Can have, but again, that's the maximum number. But we probably won't go into that number, because just having a large number doesn't solve our problem, because it requires other things. It will probably do a lot of work on context switching. Operating system will keep switching contexts, and it will take some more time. So overall, the performance will be lower. So even though we can hit this number, but probably this is not the useful number, and the performance that we are trying to get probably are not going to have, we're not going to have by this number. So keep that in mind. What I'm trying to see so far, just trying to give you a picture of this. We have a web server and we have a pool of threads, and we get requests. Each request is served by one thread, and then we have a limited number of resource, which is thread, and we are basically limited by the number of thread, and that's why we have less throughput. And what we want is higher throughput. So whatever I have so far said is basically design, basically setting the stage of what's coming in a few slides. So far, if you have any questions, let me know, and then I'll move into the next slides. All right, so I had a few demo over here. The demo is basically same thing what I have discussed so far. If you have a web application server, this is a very basic web application server. Like it can handle it opens on port 808 and then waits for a socket to connect. Once a request is request gets into it, and it's just serve it. So it's a very basic application server. And it's definitely single threaded. So at a point of time, it can only serve one thread, which is not super useful, right? We need to at least serve more than one, right? Otherwise, we would not call it a web application server, right? Web application server is supposed to serve a lot of requests. So we can quickly make it turn into a multi-threaded web application servers, which is the case for all of our modern web applications, which is we have a pool of threads, and every time we get a request, we give that request to a threads. So this is what we do, and here is a basic DDoS attack. It's a basic program. You can try out on your machine. What I did is I'll keep running this program, and then I'll start this program. So this program will basically do is, let's say, create a 20,000 of socket and try connect to that server, that basic server. What you will see is after a certain time, what you will see is you'll probably not be. So this program, what this program would do, every time I'll get a new request, it will create a new thread, right? Because over here I use new cast thread pool. You can do otherwise. For example, create a new thread each time. Anyway, so it does the same thing. We can if we do use executor, it just we don't need to do a lot of things by our hand. It's a standard API and high-level API, so we should probably use that. Anyway, so what this program would do is it will send 20,000 requests, and every time it will get a new request, it will try to create a new thread, and after a certain time, memory will it will get a out of memory exceptions, because it will not be able to handle 20,000 of requests, because it definitely will not be able to create 20,000 of threads because of our limitations. So same thing, same program. So with this program, now we see the problem, right? With this program, here comes Project Loom, right? So I'll go into details what is Project Loom is all about, how it's done, but just bear in mind. I'll just change one line of that program. So look at this program, what it does. Let me explain. It creates a server socket, in wait on a port 808, and then every time I get a request, it just submit that request to executors, which is basically the same thing, giving to a new threads, right? So this program, I'm just going to change one line over here. If I can mark it, I don't know how. Sorry. If there is a, let's see. Okay, I don't know how to mark a particular line. that's okay. So just keep that in mind over here. Sorry, I think I will be able to mark this way. So this line basically, right? If I mark this line and I will change like this. So nothing else changed. I just add executor.new virtual thread per task executor. That's the only change I did. And then if I run this, the other code, which is this DDoS attack, it will run just perfect fine. It will not complain. It will not throw exceptions. It will just work just fine. So that's definitely interesting. What magic this new line done? That's what I'm going to explain now. So that all since the beginning until this point, I just set the stage for this particular moment. All right. So I wish I could demo it over here, but if I want to demo it, probably the Zoom will collapse and will not be able to continue the discussion. So just I'll share with this slide with you all, and you can try by yourself, and probably will have the same experience what I had. All right. So what is Project Loom all about? You can see that with seeing the picture, it's basically you can create a lot of threads. How about I do a quick demo with you? Do we really can we really create a millions of thread or not? So I have a demo over here. Let me see if I can show the demo. Okay, so don't get nervous about this code. It doesn't do anything. I'll just explain. So what I did is, you can see this is a while loop, right? So what I did is I created a new virtual thread. So to create a new virtual thread, that's the method. I'll talk about that in a minute. And then I have created a counter which is long header. So every time I'll create a new thread, I'll increment it, and then I'll park that thread. That's it. So over here, I just print a number, how far or how many threads we have created so far, and so I definitely don't want to print every time I created a new thread, because that will be cloud the whole terminal. So that's why whenever I have created 1 million thread already, I'll just print the number. So that's the number. So if I run this, let's see what output I can get. So you can see I have created like 13 millions of that on fly, and then it will keep running. So now you may ask, how we can create this much of threads. The interesting part is, even though it's creating a lot of threads, and then it also gets garbage collected. So I mean, we can create gazillions of threads like this, but again, they are going to be garbage collected when they're not being in use. But theoretically, we can definitely create more than 1 million at a time. You can see that, right? So that's the interesting experiment, and a lot of people did this experiment in many different ways. So I found this particular example over here, which is I definitely want to share with you, which is you probably know already who is Heinz Kabus. He is the founder of the Java Specialist newsletter, and I love his newsletter. So he does really interesting experiment with all the time. So if you want to know about deep if you want to go into rabbit hole on a particular topic, definitely follow this guy. Follow him. So all right, let's go from here. So basically the highlights of that demo is, using this project Loom, you can create a millions of threads, and these threads are cheap, lightweight, and they are called virtual thread. And that means the throughput, the problem of throughput that we are discussing earlier, it's no longer exist with this with this new piece of technology, right? All right. So I mean, there are other benefits which is I'm going to discuss now, but so just keep in mind is that Project Loom allows us to create millions of chip lightweight virtual threads. So now, does that mean we are not gonna use the traditional threads anymore? Well, when this Project Loom is going to be in our JDK, which is available now as well. You will find this in JDK 19 and 20, but they are under preview feature. So you have to enable preview. You will probably not be able to use them directly. The purpose of having under the enable preview flag is basically you can try and experiment and make sure you don't use them in production because it's not final yet. So anyway, that doesn't mean that we're going to throw away these our traditional threading system or threading model. We're going to keep that as it is, and additionally we're going to have virtual threads. So we will keep both threading model. And now that we have two type of threads, we can call them differently. One is definitely virtual thread, and we can call them user thread as well. And it's entirely Java construct. So when we're creating millions of virtual threads, operating system doesn't know about it. Operating system doesn't see virtual threads. So it's all entirely Java construct. It's like another Java object. All right. So what we're going to call the other threads, which is classic, traditional thread, we can name it different thread. We can call them native thread. We can call them classical threads, traditional threads. We can call them even platform thread. We can call them carrier thread. I'll come into the point why we're going to call them carrier thread in a minute. So keep that in mind. So now we have two kind of threads. One is virtual, another is traditional, classic, native, whatever name you can call it. All right. So all right, I'm gonna show this part in a demo so that it is fun doing experiment with IDE. So over here, so if you want to create a virtual thread, interestingly, for virtual thread, we don't have a new virtual thread class. It is inside, but as a programmer, as a developer, we're not going to get two kind of classes. One is for threads, another is virtual threads. We are still going to use the same class, which is thread, and there are some factory method available now, and we can use those factory methods to create virtual thread. So if we want to create a traditional classical thread, we can still use new thread, and we can pass a lambda expression over here, something like that. Hello world, and running on thread dot current thread, right? Sorry, that. So, and we can call start. Maybe we can keep that in a variable so that let's call it t dot start, t dot join, so that it keeps over here until it finishes. So that's a definitely traditional way of creating threads. And the other way is if you want to create a virtual thread, what we would do is over here. So we'll use these. There is no way to create a virtual thread using this method. I mean, using the new operator and the constructor. That's one of the limitation. Also, at the same time, it's not a limitation. This is how they intended to create virtual threads. All right. So you definitely use this factory method. So thread.ofVirtual, which is basically it is developed in a builder pattern. So it's super useful. All right. So thread.virtual thread, and then you can call .start directly, and it will immediately start. And if you will get a reference of thread, which is same thing, which is thread, the Java-like threads we have been always using. So in a way, thread and virtual thread are pretty much the same thing, and they are going to behave same way. And as a programmer, we're going to treat them same way. We're going to debug the, we're going to use the thread same way. Like we're going to debug. We're going to get a thread dump the same way. We're going to use the thread local the same way. We're also going to deal with them the same way basically, but there's certainly distinction. And if you want to create virtual thread, we're going to use this method. Okay, so since it's going to start immediately, we can join on over here. Otherwise, if so over here, this curly brace to this curly brace, we have main thread, right? Main thread is going to execute all of these things. So what main thread does is create a new thread and hand over all this code to that thread. If we don't join over here, so what would happen is main thread will execute, create those two threads and die out, and it will not able to see the result. That's why we're gonna join. So we'll ask main thread, wait, let them finish. So if I run this, and as you can see, this one is traditional thread. How about I copy this line over here and see what it prints. As you can see, it says I'm running on virtual threads. So it's a traditional thread, classical thread, and this is the virtual threads. I'll explain what it is in a minute, but for now, this is this is the way of creating virtual thread. So now it immediately start, right? If we call this start method, what about if we don't want that? We can call unstarted method, which is I'm gonna get a thread, but it is not started yet. So I can call the start method separately. That's also the same thing. Now that we have a new fancy way of creating virtual thread, what about a fancy way of creating new thread? The classical thread, right? It makes sense. We can keep the API consistent. So that's also available, which is thread dot off platform thread, which is basically the thread that are not virtual are platform thread. So we can call this off platform thread, and we have both unstarted and start method. If we call this start method, and we can the thread will start immediately. And if we don't want to start, then we call it unstarted. So same thing. So that's a new additional API, which is super useful, I find. And yeah, so now that there are multiple ways to create the virtual threads. One is definitely this one, and the other one is if you don't want to go into this started, unstarted, and call a chain of method, you can just call thread dot start virtual thread. So simple, one method. So that's also available. All right. And if you have a what do you call, if you have a code base with the executors, for example, if you probably all of our code base in will have some way use of executors, right? We will write new fixed thread pool or the other variation of it. For example, if we have fixed thread pool, that means this thread pool will have 10 10 threads in this thread pool, and we keep submitting, right? Thread pool dot submit. So we're gonna submit a new task over here. So we might have the code base like this, and I'm sure we have. So what if we want to replace this whole thing with the virtual thread? So over here you can have like 100 of code, right? 100 lines of codes. So we don't have to change any of this. What we can do is we can just change one line, which is I showed earlier, just new virtual thread per task executor, and we don't need to put any number over here. So what it means is whenever we submit a task to this executor, it will create a new virtual thread and execute those tasks under that virtual thread. And once it is done, virtual thread is gonna die out, and it will be garbage collected. if we submit another task, it will create another virtual thread. That's the idea. Okay. Now, since we have billions of virtual threads, we don't need to, pull them, or we don't need to keep them, idle. So we can always create a new virtual thread and, give the task to it. All right. So these are the ways of creating virtual thread. Give me a second.
So I have a question.
Sure.
Okay, so I haven't worked in Java for a long time, but so if it's a dumb question, yeah.
Sure. No worries.
Okay, so so we used to work with 100 threads, or like we used to cap it because when it comes to concurrent programming, it also depends on the memory of how much your system can work on, right? Like how much memory your system has. So basically, if you have a zillion threads or a million threads going concurrently, right? It also depends on how much memory those tasks is going to take, right? Because if million threads are running at the same time, working on zillion tasks, okay, there could be a scenario where you will run out of memory, right? So don't you think we should cap it? At that point.
So yeah, that's definitely a good question, and your assumption is correct, right? I mean, we should definitely cap it. The thing is, virtual thread is like the another Java object. So if we have, let's say, in our regular program, let's forget about concurrency or threading. Let's say, if we want to create a for loop, like let's say for loop with a 10 millions of items, right? And we keep a new object over here. We create a new object each time. And if we run this program, there is a chance that this simple code also, give you out of memory, because there is no memory available to, allocate in your heap. So when you keep creating new object, ideally internally JVM would try to garbage collect and try to remove unnecessary object in the heap. So it will keep garbage collect running and try to allocate this object. And if it doesn't find any any other memories available in the heap, it will throw an exception, right? If this is true for this particular piece of code. So it's the same thing, similar for the virtual threads as well, because virtual thread is not a actual thread. It's a Java construct. You can call it. You can think as a simple Java object that does certain things, does certain magics, which I'm going to explain in a minute. But the parallel are the same thing, basically.
Yes, I totally understand you. Yeah, but what I was thinking was maybe the probability of getting into a system crash is much higher when it comes to virtual threads. Maybe I don't know, because I haven't read much about it. I mean, I heard about this, and it's an interesting concept, actually.
Right.
So yeah, and also how is this this thread pool, virtual thread pool? I mean, this whole construct different from our existing like executors or something? I mean, does it have a much improved thread management system or something which does a lot of garbage collection and stuff? I mean, how is it spawning these many threads?
Okay, so I'm gonna touch all of those in a minute.
Okay.
Just if you wait, hopefully we'll get those answers. I'm gonna explain how it works behind. So for now, you can think it's a Java construct. It's pretty much pretty much like any other Java object. So if you allocate many, it will be eventually garbage collected. And yeah, that's the basic idea. But I'm going to get into the internal in a minute. All right. So these are slides, basically what I have shared so far. All right. So I am using Java 19 for this virtual thread, and if you want to run them, you have to use those in additional flags. If you want to you compile code that has virtual thread in it, you definitely have to enable preview, and then if you want to run enable preview this flag, you have to add this flag. Also you can directly run them using this the third command option. And if you want to experiment this in JShell, you can also do that. That's also available. So if you want to try out, you can try out. And if you want to use IntelliJ IDEA the way I'm doing it, what you have to do is you have to go to the configuration, and then you have to add enable preview over here. So that will do the tricks in IntelliJ IDEA. And also, obviously, you're gonna need to have what do we say, JDK 19 or 20. So from JDK 19 and onward, it has virtual threading. Okay. So moving on, now the question gets to be how it works, like your original question. How we're gonna how it eventually works. We're creating a lot of millions of threads, and how it's gonna help. How it is different than our traditional traditional threads. So like earlier I said, the traditional threads are basically our native thread, basically operating system managed thread, right? Java thread are basically the wrapper, thin layer. So operating system handle all those things. For example, scheduling. If you have many threads, we have to keep scheduler is going to give one particular thread a particular moment of time, and then it will keep scheduling. It can be round robin based on operating system and their algorithm. It may varies, but most of the time, most probably it is round robin. I don't know. But how about the virtual thread? So virtual threads depends on two things. One is a concept called continuation, which is I'm gonna talk in a minute, and then another is scheduler called fork, join, pull. So these two things, works internally to make sure virtual thread that way it works basically. So let's go into a continuation a bit, then I'll talk about the scheduler. So I have a demo over here for continuation. Continuation basically is Java class. It's a Java construct, nothing fancy, but it has an interesting way of dealing certain things. So let me see if I can show you a demo. So, all right. So continuation is definitely a class, internal class of JVM. I mean, internal class of JDK. So as a developer, I'm not supposed to touch that continuation, or I should not use that. It's an internal API. Virtual thread use this continuation API, and as a developer, I should definitely not touch it. So that's why it's internal. It's on JDK.internal package. But you can definitely forcefully use them using this additional flag. So that's I did that to show you the demo basically. All right. So as you can see, it's not nothing fancy. It's a continuation is basically a class, Java class. It creates a scope, and then you can pass that scope. Inside that scope, you can say put a runnable, which is basically over here is a lambda expressions. So that's it. And continuation has a method called run. If you call it run, it will run. So you can think that is the way we do in thread, right? We submit a task, and that's it, and it is executed. Inside runnable, whatever we put, it's going to execute, right, from top to bottom. So it does the same thing over here, from this curly brace to this curly brace. Whatever we put over here, it's going to run, and this whatever thread we put this code in, it will be executed by that particular thread. So over here we don't have any other thread, right? So this curly brace to this curly brace, basically main thread. We know that, right? Main method is executed by the main thread. So all this code is going to be executed by the main thread. So there is no other involvement of thread in this particular code. So now questions get to be read a little bit, over here. So these are the codes basically we're going to execute, right? The first line, which is C1, and then second line, which is C2, and in between there is a method called continuation.yield. I'll explain that in a minute, but for now, this is just a method call, nothing fancy. It doesn't do anything, and it has no side effect. Think like that. Okay, so over here, now over here, I have a method called I have a statement which is start, and then I'm calling the run method of this continuation, which is continuation.run, and then I have another statement. Like over here, I have another method call which is continuation.run, and then I have a I have another print statement. So the question has to be for all of you who are here, let's do a mind debug. If I run this program, what would be the output of it? Can anyone guess? So yeah, so think about if it was a thread, you run a this is the runnable, and then once this is done, you are here, and then you call continuation.run, and you are here, and there's another statement. Basically, it's going to execute line by line, right? Since all of them are in the same thread, and we are not creating any new thread over here. Any idea? Just to do let's do a little exercise together. You can write on the chat, or if you want to speak with me.
I was just going to say, if folks are comfortable just writing it on the chat, they should do that. Praveen, I see you're coming off mute. Did you want to start the conversation? Maybe we can all.
I mean, I'm not very familiar with continuation, but then shouldn't they just print usually? I mean, if I understand this, maybe it should just start with printing start, and then maybe with the run, it would run the runnable, and then just print all those stuff, then come back and done.
Right.
I don't know, and if
okay. Think about you don't have to understand the continuation for now, but think it's a simple Java program, read line by line.
It seems like, I mean, you said virtual threads use continuation, so shouldn't it be like two separate threads, like one for the main thread and one for the continuation? No?
For now, forget about virtual thread or anything. For now, think about this is just executed by the main thread. So over here only we have one thread, which is from this curly brace to this curly brace. We don't have any threads or anything. It just probably if we would write all this statement one by one, it would probably execute the same way. We have just introduced a new block, new ideas, which is continuation, but it's just Java class for now. And if we execute this, what would be the what do you think, basically? I mean, you can be wrong, and that's okay. You can be right. That's superb, definitely.
Will it print start C1, come back C2, done in that order? Or
and there is one more continuation in 23.
Over here, you can see
the same steps as what you just said or not. I'm guessing to the same thing. Start C1, C2, come back C1, C2, done.
Okay. So all right. Yeah, you were saying something.
No, I was just going to say, Renat, basically this the line 23 is all that I was thinking of adding. That's it.
All right. So yeah, I mean, that's essentially it should, right? But if you run it, let's see what output it brings. Okay, so what I have to do is
okay, I wasn't expecting an exception.
Okay, I was not as well.
Okay.
So what it's saying is cannot access continuation. Okay, so what I have to do is I have to copy this line and add this over here. So first of all, I have to enable. Let's see if I can do that. So if I run this, okay. So as you can see, interestingly, it did start and then C1 and then come back and then C2 and done. So, so what I have to do is I have to copy this line and add this over here. So first of all, I have to enable. Let's see if I can do that. So if I run this, okay. So as you can see, it did start and then C1 and then C2 and done. So, so what I have to do is I have to copy this line and then add this over here. So so when we did the first run, it didn't print the both C1 and C2. You noticed? So what happens is, interestingly, this continuation does is, let's say you execute. So you are over here. So first statement is executed, and then you call continuation.run. So this is going to execute this line first, line by line, and then it execute the yield operation. What it does is, the yield operation is it suspend the execution. So we get it out from this execution, and so this, since continuation.yield, we called it, suspended the execution. Basically, it should execute a whole 3 line, right? But over here, when we call this method, it suspended the execution. It came immediately over here. So it was able to execute the first line and then came over here. So execution, from there it came over here. And then when we call this again, what happens is, it didn't start from the beginning. It started from where it got suspended. So it started the execution over here. So it already executed the first 2 lines, so it doesn't need to execute the first 2 lines again. Rather, it will start immediately from this line. So that's what happened. And continuation is basically does this thing. So that what essentially it means is, let's say it is executing something, and middle of where it see a call, which is continuation.yield, it can suspend its operation and go away, and it can whatever thread it's executing. Let's say I'm executing from the main thread, right? I'm executing this piece of code from main thread, so it gives the execution back to the main thread. So over here, this line I'm executing on a main thread. Now I'm calling the continuation.run. So execution goes over here. I'm still on a main thread, but when I'm calling this yield, it's just giving me back to the next line, which is I'm calling over here, which is come back. So keep that in mind. Now let's say I'm inside a virtual thread, and whatever task I'm give to virtual thread, it is going to wrap by a continuation. Okay, so now let's say over here, I'm executing some work, and then over here I call the network I operation, which is I operation. I call it different service, which is which could be waiting for a microservice. So whenever it happens, I have to in traditional thread it will wait until we get the result, right? So in continuation, what it will do is, it will not wait over here. Rather, it will get suspended. This virtual thread will get suspended, and the execution will be given to the original thread. Let's say I'm running a virtual thread from a main thread, which is native thread, like the operating system thread. So since all of them are Java construct, right? So this execution has to happen by a thread, which is a native thread, right? Because think about this whole virtual thread is a Java construct. It's a Java method, and someone has to execute all of this code, and thread is the execution environment. So ideally, internally, what happens is, all the virtual threads get executed by our traditional thread, which is our classical thread. So basically, classical thread carry the virtual threads. It happens like one thread can now execute a lot of virtual threads. So the idea is, let's say I have a classical or platform threads, and I'm given a virtual thread to it to execute, and it's executing, and whenever it sees a IO operation or blocking operation, it suspends itself and it goes away from the picture. So now thread is free again. So it can pick another virtual thread and keep executing, and it's the blocking operation, and it suspends itself. So let's say it's a IO operation, right? And now when this virtual thread is basically suspended, it's somewhere in the heap. The thread it's executing, the original thread, which one was executing this particular thing, is not waiting for anything. It can continue working on other threads, right? So ideally, although the virtual thread is waiting on the result and it's suspended, but the original thread, which is our native thread, it's not wasting any CPU. It's keep on executing other virtual threads. So this way we are basically tackling the the blocking operation. It's still virtual thread is blocked, but it's not consuming the CPU. Our threads are free, and our threads keep on continuing executing other virtual thread, other things, other tasks, whatever it's executing. So that's essentially bottom line highlights of the virtual thread. So it uses continuation. Continuation can arbitrarily suspend itself, and our traditional classical thread keep on working, and it's not wasting on CPU. And over here, when I say that it's based on two things, which is continuation and scheduler, so it used the fork join pull. It was added in Java 8. So basically, fork join pull will start with the number of CPU available on your machine. For example, this computer has 10 CPU core, so it will start with 10. And now, if we have, let's say, millions of virtual threads, the number millions is basically exaggeration. The idea is we are probably not going to use millions of threads in a production environment or in a real scenario. It just give you a context that we can theoretically create millions of threads and we can achieve that much of throughput. But we'll definitely in real use case, it's definitely going to differ, and it's definitely going to be we're going to keep on testing what is the sweet spot. But again, think about as a task. Virtual thread is basically a task, a runnable, something we want to put to this thread scheduler, and the scheduler, this fork join pull is going to get a thread, virtual thread, and keep on executing. It sees a blocking operation, it suspends itself, it goes away, takes another task, which is another virtual thread. And when it's executing its blocking operation, it goes away. And then those virtual threads which are suspended, they will be resumed later when there is a result. So let's say it is waiting on a IO operation. When IO operation is done, it will get notified and it will resume again. It will get chance to be executed. But the fork join pull that's executing all these virtual threads are always busy, always executing. So our CPU is not wasting. Our CPU is not waiting. Although we are running on a few threads, which is, let's say, 8, 10, can be 12, but it can execute like millions of virtual threads at the same time. And if they are blocking operation, they are waiting, and our threads are not waiting. Rather, the virtual threads which are suspended, they are waiting on, and we don't care because they are just another Java object. And when there is a result, they will resume. They will get chance again to be executed. So now reiterate from the beginning. Let's say we have a lot of requests coming, and they're all IO driven, right? So every time a client comes to the server, it will give the task to a virtual thread. And definitely this task probably needs some sort of IO operation, right? For example, it needs to talk to database, it needs to talk to a microservices, and whenever it needs a blocking operation, it will just get suspended, and it will serve another request. So that's the idea. And so it's especially important. We have to keep in mind that virtual thread is designed in a way it can deal with IO intensive operation. And what about the CPU intensive operations? So interestingly, virtual thread is not designed for CPU intensive operation. If we have CPU intensive operation, we can just use our traditional threads. And for CPU intensive work, virtual thread will not add additional value. Probably it will add some extra things. So we have to keep that in mind. Virtual thread is especially important, useful for blocking operation, essentially in IO intensive operations. All right. So this is basically size for continuation, which I already showed you. All right. So let me know if you have any questions so far. I have a demo over here, which I can probably show you. There are certain problems with virtual thread still, which is we can discuss later. But let me show you a quick demo, which I did earlier. Let's see if I can show you. Okay. So let's say this is a URL where you can download dumb images, basically random images. So it's definitely a network call, right? So if you want to call download 10,000 images or 1,000 images, traditionally there's I did 2 way. One is using the virtual thread, another is the thread pool. So let me the traditional way. Let me show you the traditional way. So let's say I have created an executor with 100 threads, like you said, a cap. We have a cap over here, which is 100 threads, and in this pool we have 100 threads. Now in a loop, we are submitting the task, right? We have a list of URLs over here, which is let's say 1,000 or 10,000, doesn't matter. And we're in a loop, we're submitting those tasks into the thread pool, right? So let's say we submitted all of those in a loop. But what happens is, since we have 100 threads available in this thread pool, at a point of time, only 100 URL can be fetched, right? Because let's say I call a URL and there is a waiting time, there is a network delay, latency over there. Let's say 100 millisecond delay for each fetch operation from the network. So one thread comes and it will call this API and it will wait. This 100 millisecond probably it doesn't do anything, right? It just call an API and it waits, and probably 90% of the time this particular thread is waiting on to get the result. So if we if we have 100 threads are basically waiting 90% of the time. They're burning the CPU and wasting. They're not doing anything. On the other hand, over here, which is I'm doing the same thing with the virtual thread, right? Sorry, not this one. So this one, right? I'm doing exactly same thing, right? But over here, whenever I'm submitting the new task, I'm creating a virtual thread. So let's say whenever I submit in this this one, so I'm creating a new virtual thread, and virtual thread hits the IO operation and it suspends itself. It goes away from picture, and the native threads or the carrier threads that's running this virtual thread is free now. It can take another task, which is another virtual thread, and it will create a virtual thread and hit the network call, and it will again, it's a blocking operation, it suspends itself. So any moment of time, this fork join pull thread that's running the virtual thread are not wasting time. They're just calling the network. And I did the experiment, and I definitely got a great results. If you want to try this code and experiment it out, so the benefit is in this code there's no wasting of the thread or execution or CPU. Over here, in the traditional, there are a lot of waiting, which is basically wasting the CPU, and threads are idle waiting to get the result. So these are the benefits of virtual thread.
Bazlur, where is this code available? Did you put this on GitHub or?
Yes, I can definitely share that in a minute.
Okay, yeah.
It's available on GitHub and the slides as well. Let's see if I can share with you.
Okay, that'll be awesome. Also, did you say the minimum version is Java 19 for this?
Yes,
to
this
take
minimum
benefits?
version.
Yeah.
Yes, this minimum version is 19.
Okay, got it.
All right,
I also have one question actually.
Sure, go ahead.
Okay, so you did mention we use we should evaluate when we should be using virtual threads. Like you said, it's one of the main use case here is when we have intensive IO operations, when that's happening, that's when we should consider. So we have a C# backend, and an initiative what we have been doing in our company was moving away from and our operations are basically IO intensive. So what we have been doing was moving from synchronous code to async code, and that has been helping us actually tackle many of this, unblocking, blocking, and like removing and just making sure when none of our threads are blocked. So can I say this virtual thread is also doing something very similar to what our async code, what we have? I mean, I think maybe I'm just not.
Okay.
Yeah.
I understand your question. So
Okay.
there are multiple ways to solve this problem, right? So what we're trying to achieve is our threads doesn't wait or doesn't block our code. If we have a blocking operations in our traditional way of doing things, we have a problem, right? Because thread is going to be blocked for a momentarily, and we want to avoid that. So to solve that, I mean, I don't know exact implementation what happens in C#. There are various implementations. For example, there is a implementation of having callback like in JavaScript, right? So idea is, let's say, something takes time, so I'll give a callback method. When it is done, it will call myself, right? So the problem with that approach is it keeps on getting, there is a callback hell. There's a concept called callback hell, right? You're probably aware of that. That's sort of scenario happens. And the other way is there is a reactive programming also available, which is deal the same thing, which is what do we say? Solve this blocking problem. Reactive programming has a lot of other offering as well, but essentially it does the same thing, which is avoid the blocking operation. And the availability of Java, I mean the asynchronous programming, which is basically through the executors, right? We submit a task and wait for the future. So let me give you a quick example over here. I'll get back to your answer in a minute, but let me show you an example over here. Let me see if I can show you that. So think about this program, right? So we want to calculate credit for a particular person, right? We have a person over here. We can call this assets. We can call this liabilities, and then we want to do certain things over here and then calculate credits. So this is definitely a network operation, IO operation, because it goes on a database and fetch the result. It can be a microservice. This is also an IO operation, right? So over here, so from this line to this line, we have a thread, which is when we got a request, we give this method to a thread to execute from this curly brace to this curly brace. So now this thread is basically executing line by line. So when we are in this line, so we are basically doing what we're doing. We are calling the IO operations, and we're waiting for this result over here. And then same thing over here, we are calling this method, which is get liabilities, and waiting for the result. And then we are doing something over here, and we are also calling this calculate credits. Probably it also does invoke another IO operation. Let's say, for the discussions, maybe something else. So this is basically, if this one takes like 20, let's say 200 milliseconds, this one takes 200 milliseconds, this one takes 200 milliseconds. And if we do this all serially, the whole method will take like 800 milliseconds, right? But if we could, asynchronous, there is a some programming method called allow something like async. I am not familiar with that, how C# does, but probably C# does similar things.
Yeah, that's exactly what we do. Yeah.
Yeah. So we can do that, right? So if we call these assets, and because for over here, calculate this credit, we need both results, and these two methods can be executed parallelly. If we can have that, we'll have a performance benefit, right? The time will, for example, if this two call done parallelly, so we'll able to get get this result in 2 milliseconds, 200 milliseconds instead of 400 milliseconds. But again, when we are calculating the result, we need both results. Over here, again, we are so we need probably the get operation, the result to get the result. Over here, we also need the get operation. Still, so we are dependent. Over here, this is definitely a blocking operation. We cannot avoid that because we need the result. Otherwise, we cannot calculate the credit. So there is no way to sort of avoid that. But we made some progress. For example, instead of 800 milliseconds, we made it is now 600 milliseconds, which is definitely a progress. So there are some approaches, for example, make it in Java, there is things called computable features, which also does the same thing. The benefit of having computable feature is now, this can further improve. And we also do certain, functional approach. We can compose and other things. But again, think about this code, right? This is probably you need a complex mindset. I mean, if there is a bit of learning curve as well. You probably have to know the functional programming, or you have to know the computable features and other things. The other problem is, which is this code is not atomic anymore, right? For example, this computable feature can fail independently because it can be executed in another thread. This computable feature can fail in another thread, even though they're being executed by a different thread. They're not related. So if you take a thread dump and if you have a problem, you'll probably not be able to relate them if there is no parental relationship, right? So those are some problems already there, and you need some mental gymnastic as well. And also, if you want to do reactive programming, there are certain limitations. For example, like this one, definitely you need a learning curve as well. And when you read the code base, it doesn't feel intuitive. It doesn't look imperative anymore. Basically, we're creating a lot of pipeline in a way, and the way you are reading, it is not executing the way you're reading, right? It's executing some other ways, which needs certain mental gymnastics to figure out. So it becomes complex, and those definitely solve our problem. For example, the blocking operation, it gives us preference, but again, it loses certain ability. For example, debugging, and if we need to, preference, if you want to run, profiler, it's also give us some problems because in reactive programming, you will probably not get accurate result if you profile them because you don't know how many time are taking this particular method because you don't know which thread is executing this particular method. So those are definitely some problems we have. What virtual thread is solving is giving you is you don't need to, blocking is free over here. So you need to worry about blocking. You can just, do traditional work, which is, imperative work line by line. The way you are seeing code, it is executing exactly. And since, it is intensive and blocking, and we solve the blocking problem. So your code becomes traditional, simple, and easy to read. So these are the benefits of virtual thread, basically. I don't know if I'm able.
Yeah, gotcha. I mean, I think it's a more cleaner approach.
Right.
To understand also, yeah, makes sense.
Yeah. So I have an example over here. Let's see if I can show you. So think about this one, right? Two code over here. Each of them basically, downloading like 10,000 images. And this was a way of doing asynchronous in Java. This was also in Java, but this one is basically traditional way, imperative, line by line. So if you want to explain this two code to a beginner, let's say a new developer came to your team, which one you will be able to explain easily? Left or right? I would say the right one because it's easier. It's you can just read the code and understand the code what it does. But the right one, it does probably the same thing, but you need certain gymnastic because it's not it's a functional. It's it's creating. For example, the computable feature is basically a box, right? You have to if you want to do multiple asynchronous thing, you have to stay inside that box. So there is definitely a learning curve, and there are other problems as well. But I understand this approach, for example, Reactive and Async approach that you mentioned. I have no idea, but those are definitely attractive. But if you want to keep a maintainable code for long run, I would probably vote for the right one because it's intuitive, it's easy to read, and it's simple. And our main problem, which is blocking, goes away over here with the virtual thread. So that's all I have. I mean, I had a lot of other things, but I'm not sure we have time for that. But again,
yeah, I was just going to say that we do have like 2 minutes left. So if folks wanted to at least ask questions about what we've just had, I think Praveen and others, like we've been asking as we went, as we, were going through the presentation. So this was a great introduction though, Bazlur, like just in terms of like what is threads, what are threads, like what are they made up of, how are they made up of in Java to where we are right now.
And learning more about virtual threads. And if you had a lot of content, maybe we can have you back at some point to cover the rest of it. But we can cross that bridge later.
Yeah.
There's another interesting concept, which is in a incubating API, which is called structured concurrency, which is another fascinating topic.
Oh, nice.
Which is basically based on the virtual thread. Maybe in some other days we can discuss that.
Yeah, we can do a part 2 of this. This is a hard topic, and it's like just setting the foundation itself, like took some time. So
any specific good resource which you would recommend us to? I mean, if I have to read more about it, would you recommend something?
Sure, I have these resources available in this slide, and I shared the slides and code base with you all in the chat. You can definitely go over here and read more about this.
Oh, awesome!
I also added a few presentations. Some other folks did. So you can watch those presentations as well.
Praveen, I also added the GitHub URL to our meetup event. So if you ever wanted to reference back, then everyone should have it. You can just go back to the meetup event to find the slides, and we'll also have the recording up on our YouTube channel soon. So
yeah, I'm browsing the web right now. So thanks.
Awesome.
All right, so that's all I had for today. Thank you for your, I got really some attentive listeners. That's definitely, and I got some good questions as well. So that's definitely rewarding, and I enjoyed talking to you all. And if you want to, get in touch with me, there is a Twitter account, which is easy. You can just, send me a tweet. I'll be able to get in touch. If you have more questions, feel free to, ask that way. If I don't know, that's an opportunity to learn, right? So I'll definitely try and dig into it and, share it with you all again. So thank you, everyone.
Thank you so much.
Thank you so much.
Yeah, thank you so much.
Thank you for, speaking to us today and showing us a great topic. It's definitely, piqued our interest, and we can now go and read more about it. Thank you so much.
Thank you.
And thank you to everyone who attended the session as well. You should be looking out for the, the YouTube channel presentation, upload, whatever, the notifications.
Yeah, we should have the video uploaded at some point, either this weekend or next week.
But yeah. Sounds good. Yeah.
Thanks, everyone.
Thank you, everyone. Have a great evening.
Thank you. Bye.
Bye.
Bye.